All right, good morning, everyone. So I just wait until all of you have come back, and would like to have taking the attendance first of all. Let me see. Just wait. All right. Today's is day 5, right? Day 5 now. And all right. So Cam 1 from I start from 4 student from 4A first, okay? 4A. 陳許婷
喺度。
morning. And 長學家are you here? Not here. 陳學家
Yeah.
Yep.鄧家傑
喺度。
Yep. 何偉林
喺度。
林俊軒
喺度。
林成漢Yep. OK. 李佩恒
喺度，
任俊熙
喺度。
鄧浩俊
喺度，
黃俊熙黃奕朗
喺度。
鄭學明Cyrus, are you here? Oh, not here. 張思維not here. 馮家謙
I'm here. Hello. 張思維。
係 OK. 馮家謙 are you here?
I'm here.
何孝日
喺度。
何麗妍
喺度。
郭俊熙
Hello.
係朗力
喺度。
李晴
Hello，
梁家傑
喺度。
李格星
Hello，
係李建樂
喺度。
馬家樂
喺度，
吳漢一
喺度。
魏俊滔Yeah, I can see your message. OK. 譚君柔
喺度。
黃成軒
喺度。
Okay, all right. So once again, I need to call upon 鄭學明. Are you here? 鄭學明, are you here? No? Deng Hongming not here. So we would have a start of the lesson. Last time I asked you guys to finish one questions about the electrolysis of molten lacto-bromide. Okay, do you still remember that one? That questions. Okay, so last time I just stopped here to tell you one compound is very special. It does not just conduct electricity at molten state or in aqueous solution, but also there may be some chemical decomposition. Okay, so this is what you stop at here. Okay, last time. Do you still remember that one? Okay, so and before that, I ask you guys to refer to the exercise, right? And have a try on that. Try to understand in terms of chemistry what really happened. Now, could you please go back to this page? Okay, you know where is the page 107, the chapter exercise. Okay, question 25. Okay, last time I asked you guys to have a try on it. Okay, let's check if you know how to answer that. I will pour upon the students of the list. Okay, on the lists of attendance, and I would if you can, I know that not all of you would have a mic. It doesn't matter if you have a mic. You may turn on the mic and tell your answers. And if you have got a pencil, what I mean is Apple Pencil or any other pen for the tablet, you may also write down the answers on the screen as well. Can you get my point? So because I want to. I would like to make the lesson a little bit more interactive, so I would like you guys to have that type of arrangement. Do you understand? So, Trần Ngọc Cam, 25, A part. Yep. A part, chemical formula of
PbBr2.
Yes, this one is easy, right? You are going to relate to the how you can come up with the formula, PbBr2, chemical formula, okay? So what is that? It is not chemical formula. Lacto-bromide, this part, this one is not is not a chemical formula. We call that chemical name. It's different, okay? So B, thank you. B, Hồ Hoài Long. B, Hồ Hoài Long. Why is heat needed for the reaction? Why is heat needed for the reaction? Heat here. Why? Hồ Lâm hiểu biết. Hồ Hoài Lâm.
I don't know.
You don't know. So just imagine a case without heating. So what will happen to the top?
Nothing.
Without heating, the same result. You mean the same result? First of all, does it conduct electricity for lacto-bromide? If it's not heating, for lacto-bromide, so what is the state? Physical state at room temperature, pressure. Is it solid, liquid, gas, or what? Without heating. Do you know? Do you know?
I don't know.
You don't know. Now, actually, it comes to the concern of the chemical, the physical state of chemical. For ionic compound, most of the time, okay, what we just mentioned about the ionic compound is that just wait. Now, for ionic compound, most of the time we will say we will say it as a solid at room temperature and pressure. So last time I just talked about room temperature and pressure. Do you still remember what's that? Room temperature and pressure. So it is it is for scientists to communicate, okay? The fair way to compare, right? So which is found as at 25 degrees Celsius, 180 atm pressure. Do you still remember that term? So solid, mostly they are solid. Mostly they are solid at room temperature and pressure. So whatever different combination of lactobromide, okay, of lactobromide, or including this, it is a solid. Okay, do you understand? Most of the ionic compound that we mentioned, they are solid. So why is heat needed? So in case we have got solid, we have got power supply to it. So electricity, it is now supplying through that. Okay, but does it conduct electricity for that solid ionic compound? The answer is no. Yeah. So what is the purpose of that? Lim Jin-hin, why is heat needed? So what is the use of heat? Applying heat to it. Yes, try. If I apply heat, what will happen to the solid, to the lactobromide? You don't know. Now, I give you one more hint. That all of you, could you please search on the web the melting point of lactobromide? Do you know what is the melting point of lactobromide? Maybe some of you may be got puzzled, right? How come that solid will have got that behavior, right? Lactobromide. You search on the web. Do you know? Yeah, somebody was suggested as 300 and something. Okay, take a look. Melting point, lactobromide, melting point, can you see the term? It's just 370 degrees. See, 370 degrees. So, what is the hidden message? If I use Bunsen flame, okay, Bunsen flame, do you know what is the Bunsen flame temperature? Bunsen flame temperature, do you know? Yes, it will be raised up to, it depending on the size of the flame, the color of the flame. Okay, so you may see the temperature ranges from they will ranges from 300, 500, even 700. Okay, it depends on the brand. It depends on the brand of the Bunsen burner. Some of them may be of higher quality, so they would allow much air to supply to the chimney, such that the fire burned. Okay, the flame burned. It is completely blue. Okay, how about school? So it's not 300. It's too low. It is around 500 to 700. 500 to 700. Okay, it depends on the brand. But 500 and 700 degrees is high enough to what? Take a look at the questions again. High enough to melt. Okay, to melt the lactobromide. So all of you, could you please mark it down now here? It is to melt the lactobromide. Okay, such that, so what is the purpose? Such as, what is the purpose? You melt it.
It conduct electricity.
Yep, it can conduct electricity. So this is what you know it for B. State what we observe and each electrode, explain your answer. It's not just telling me the product form, but also the why. Tell me why, okay? So simply speaking, if you talk about this electrolysis of molten salt, we need to consider positive electrode and negative electrode respectively, okay? separately. Tell me what happens to the positive electrode and what happens to the negative electrode. So positive electrode is here, right? Positive electrode and negative electrode. So what happens to the positive electrode? Positive electrode will attract what? It will attract what particles?
Bromide.
Bromide.
Bromide ions. Why? Why will we attract bromide ions?
Because
It's
bromide ion is
negative.
negative.
Yes, negative. Yeah, negative charge. Bromide ions, they are attracted towards the positive electron. Okay, the negative. All of you, please write down. The negative bromide ion, they are attracted towards the positive electron. Similarly, you do the same thing to answer negative electron, okay? So this is the positive ion, which is Lead-2 ion. So this is bromide ion. On the other side, they were attracted towards the negative electron. Okay, so what will happen? Can you see that I write down the electrons, right? Starting from this moment, whenever you see a circuit, electric circuit, we would consider the flow of electrons instead of currents. Okay, in physics, we talk about currents simply because it is about their own tradition, the very, very old tradition, to talk about the charge flow. But in the past, they would treat the charge flow as positive. But in reality, the electric wire, do you know what makes the electric wire? What is the material? It's copper, right? The copper wire, we have got the free electrons here, okay, for conduction of electricity. So that's why whenever you talk about circuits, you may see that the electron flow is that. Can you get my point? So after we focus on electron flow, first of all, negative electron. We have got so many electrons here. So what will happen? So it will attract something positive. So what happened to the positive ions, which is Lead-2 ion, just stick onto just touches the electron? What happened?
Gain electron and become atom again.
Of electron become atom. How? Electron become atom.
I mean gain electron and become atom.
What substances gain electron?
Lead.
Lead-2 ion. Okay. So remember, you should know what is that. Okay, Lead-2 ions, they will gain electrons. Okay, at the electrode to become lead. So okay, so become lead atoms. So that's why it is a type of reduction. Okay, reduction 還原. So if you write down the equation, you may need to write down something like this to tell the ions, the Lead-2 ions, they are now reduced. Reduction 還原啦. So to form lead, in which it is helped by gaining electrons. Okay, so what will be observed actually? Can you see that, Mr. Chin? You still haven't answered anything about observe. Observe, right? Can you see the word observe? You didn't tell me anything about observe. You just explained, but you did not. You didn't have anything about observation. So what is observation?
Orange liquid.
Orange liquid.
At the positive electron.
Positive. How about negative? Now we focus on negative.
Silvery liquid.
Oh, silvery liquid. But isn't it solid? Instead, it's liquid.
Melt.
Because it's melted.
Melted.
Yes, it's molten. We call it molten. Silvery. It is something silvery. But why come it has melted? Do you know the melting point of lead? Melting point of lead. Do you know? Check it. Tell me what is that? What is the melting point of lead? Very low when you compare with other metal. Do you know? Anyone who can tell me? It's just
327.5
degrees. Yes, very, very low melting point. The melting point is just 327 degrees Celsius, very low. So when you compare with the Bunsen burner, the temperature, it is low enough, right? It's low enough to be melted. So originally we some solid, but it's too hot, which means the environment is too hot, it melts to form silvery liquid. Okay, how we describe it is liquid, silvery liquid. Can you get my point? So this is the observation that you may know. How about positive electron? I do the same thing, right? So the bromine ion, finally it loses electrons, right? Otherwise, you would not know that electrons, they will go back to the positive pole, right, of the power supply. So we will say that bromine ions, we will not say it as gain, it will lose electron. That the term is different, right? Gain or lose is opposite, right? Lose electrons to become what? The bromine atom. Is it bromine atom? Somebody may say so, right? But in the naturally occurring environment, it is no longer a bromine atom. It becomes what? It becomes bromine molecules. Okay? So we will say so. Bromine atom will soon become what? Will soon join in pairs or combine to form bromine. So why does bromine atom not go in alone, right? It loves to go in pairs. Why?
Because they need one more electron to become stable.
Yes, bromine atom itself is not stable because it is not yet octet. So you need one more electrons to become octet. But how? It's by
share electrons.
Yes, this time it is by sharing of electrons, but not gain or lose. Right? It can be either do it by gaining electrons by metal, for example, lead to bromide. Right? It seems that the electrons comes from lead to ions, right? Lost, and to form bromine to form bromide. It's one way. So, but for bromine molecules that may be formed, it is due to the covalent bond. You will know it later. So it is by sharing of electrons. So it is Br2 plus 2 electrons. So what will happen to the observation? The observation is that Br2, it is in form of a what? It is in a liquid, right? At room temperature and pressure, it's too hot. So what will happen? They will form a gas, which is also reddish brown. Do you understand? Questions? Any questions so far? So
yes.
Yep. Questions? Yeah.
If the bromide ions gain back the lost an electron, does it still reduction?
It's not reduction. For the losing of electrons, we call that is not reduced. We call that oxidized, but the term is rather difficult to comprehend for the time being. Okay, so according to our scientists, we would mention the losing electrons, that type of reaction, as oxidation. Maybe some of you may feel surprised, right? How come we call it oxidation? We do not have any oxygen here, right? But oxidation, we've got so many definitions, right? Besides using gain or loss of oxygen to tell, we may also relate to gain or loss of electrons to tell. It is oxidation or reduction. So in this case, it is indeed we are going to have a forced redox reaction. So why we say that forced, right? Is because they cannot go by its own, okay? They cannot go spontaneously. I need extra energy to separate the lacto ions and bromide ions apart, first of all. And second, it is used to decompose the lacto ions back to the original elements. Okay, so electrolysis is a very harsh method in which I supply electricity and we will break those compounds apart. Okay, they will form lead and bromine respectively. So it is a type of decomposition, right? Decomposition will require energy. Can you get my point? So without doing anything, lactobromide can stay for long. Okay, can stay for long in the chemical bottle without you treat it. Okay, without treating it, it's still lactobromide. Let's say I place it for 10 years later, right? Maybe after you graduate and try to take a look on the bottle of lactobromide, still lactobromide. Okay, which means that lactobromide at room temperature and pressure, it is rather stable. But how come I can turn back to lead and bromine? I need extra energy to force them apart. Do you understand? So it is electrolysis. You may know it in the English word as well. So you know what is meant by electrolysis? A very special term. Electrolysis. You can split it into two. Okay. Electro means using electricity. Lysis means breaking down. Okay. So electrolysis means I would use electricity to break down something. And later on, I know that some of you you will be studying biology as well, right? So you may see lysis. It is a term that it is frequently seen in biology as well. So in biology, we will use the term hydrolysis, right? So what does it mean by hydrolysis? I use water to break down something. Okay, so you will know it in biology as well. And this term in chemistry, you will know it in organic chemistry later. Can you get my point? Any more questions about this? We just talk about electrolysis of molten lactobromide. And what we will see in detail is that the positive ions and negative ions will become what? Mobile, okay? Mobile when I heat it. Mobile. Only you make the ions mobile would it conduct electricity. That is point one, okay? And it would help you explain why in we will call that as electrolyte, okay? Do you still remember the definition of electrolyte? The electrolyte can only conduct electricity at what? At molten state or in aqueous solution. And why? Because only having these two states would the ions become mobile. All of you, could you please mark it down, that term, mobile. So this is our technical term, which means freely moving. Only by having such, the ions will undergo the influence by the electric field to go in a directional way. How directional it is? The negative ions, they will go to positive pole, while the positive ion will go to negative pole. So it is a type of directional, 有方向性嘅, okay? The directional movement. And later on, what will happen? Indeed, there is a chemical change. Why? Because at that electrode, one electrode, they would help gain, they will help the ions gain electrons. So you may see on the elective electrode, okay, because it's the place where there is a supply of electrons. So that what will happen is that they would merge the two chemicals to form metal. And if you go into another pole, another electrode, in which it is the pooling of electrons, okay? So what will supply the electrons is bromine, right? Bromine, they will lose their own electrons. But once I lose the electrons, it's no longer so stable. They will form highly reactive bromine atom. So they will find a partner nearby. They will merge to form bromine molecules. And they will release, and you will see it as reddish brown gas. Do you understand? For those who can understand what I've just said, could you please put a tick? Okay, if not, across, and I would like to further clarify. And for some others, any more questions? Any more questions about the others? Lim Junhee, Lim, do you understand or not?
Yes.
Zhang Siwei and Feng Kahim, do you understand?
Yes, I understand.
Good. 吳漢一、馬家樂、魏俊滔、黃成軒 ，what do you think?
Yeah, I understand.
Good. So let me know if you cannot follow. Now, any questions so far before we proceed? So just circle this question, and you need to refer to it later because in your exam or in a test you will see that similar questions. Why do Mr. Jin tell us similar? Because I can change the chemical, right? It's no longer lactobromide, I change to some other chemical. But very often, why would you see lactobromide as a good example? Why is it set to be as a good example? Because among the different types of ionic compound, this one has a very low melting point. Now take a look on sodium chloride, and you can get what I mean. Anyone who has searched for the melting point of sodium chloride, Tam Guan Yao, do you know it? The melting point of sodium chloride. What is that? What is it?
Over 1,000.
Well, 1,000, not really. Sodium chloride melting
800.
point. 800, 700 to 800. So it is very high, right? But in the lab setting, okay, nearly 800. So in the lab setting, the Bunsen burner, the temperature of it is not high enough to melt the sodium chloride to form liquid. Okay, so we will not tend to use sodium chloride as an example to do electrolysis. Instead, we will try to use the ionic compound having lower melting point, so low that our Bunsen burner can help melt it. Okay, only by making the ions mobile, we can conduct electricity and do the decomposition process. We do the breaking down electrolysis, okay? Do you understand? Nice? Easy, difficult, abstract, or what? What do you think? Easy? Can handle? Now, so what we just mentioned, similarly, you may find it on the book on page 80. Take a look. So you may see that you are going to have the electrolysis of zinc chloride. You do the same, right? The positive electrode and negative electrode will be treated separately. For positive electrode, it attracts negative ions. So this time it's chloride ion to form chlorine gas. So it is a type of losing electrons reaction. We call that oxidation. While for zinc ions, they will attract towards negative electrode, and they will gain the electron supplied, and they will form zinc metal. Okay, so do you still remember that battery? 長正短負隅, do you still remember that one? Okay, so the electrode, the polarity of the electrode, which agrees with the polarity of the battery. Okay, can you get my point? So remember, somebody who still got puzzled about this, you should know some little knowledge about IS, right, in Form 2, before you can really understand. And second is about the flow of charge. In physics, we call about positive charge flow. So you may see, we will write down current with that direction. Do you still remember? But for chemistry, we talk about electron flow. So you may see the electron that will flow in this direction. Okay, this is electron flow. How about chemistry? We will focus on electron flow. Do you understand? So this is what we know about this. So ionic bonding, what is that? Okay, somebody would say it, would find it so difficult. Right? So what is mean by ionic bonding? Now, ionic bonding is something like this. So you, I would like to talk about what is mean by sodium chloride. Sodium chloride is a solid. So what can you tell about the particles that hold the sodium ion and chloride ion together? It must be held by form some strong attraction, right? At room temperature, the heat is not high enough to melt the sodium chloride. So we will call that the ions, they're held together by some strong force, so strong attraction force. Okay, so that's why you may find it as solid. And most of the time, when you find some other ionic compound, is also solid. So can you tell me some more about that bond, the attraction? What makes the attraction? Now, if you refer to the book, page 82. Now, this is one of the model which shows sodium chloride. Can you describe why would they have such arrangement? Why would sodium ions and chloride ions placed alternatively? Why? Why? Anyone who can tell? Lý Pui Hằng.
A stronger structure.
Oh yeah, Lý Cheng, you want to say something? It doesn't matter. Each one of you, you can try. Yeah.
Structure. It has a strong structure.
Strong structure, but yes, I know it's strong. How we know it's strong? How about the packing? Is it regular, random, or what? It's rather regular, right? Can you see that? A regular arrangement. So what do you know in Form 1 IS, right? If you talk about particle theory, whenever I draw the ball in a regular arrangement, which means order, right? It places it in an orderly manner. So what is that? We will call it as a solid, right? Yes, solid, good, solid. And we try to do something more difficult. Right? In the past, we talk about solid, liquid, and gas. We usually use one type of ball, right? This time, I use two types of ball. Sodium ions, the purple one, while the chloride ion is the pink, is the green one. And in which you may, it's not just the color to tell you the difference, which indeed, in reality, it is about the size difference. Can you see that? Chloride ions is larger than sodium ion. Do you know why? Something about this. Just remember sodium ion. I draw something here. Do you know what's that? What does that mean? You don't understand. What does that circle means here? It tells you the electrons, the number of electron shell occupied, right? So for chloride ion, we have got electronic arrangement 288, while for sodium ion is just 28, okay? So it's a matter of while you measure the ionic size as the distance between the middle, which is the nucleus, to the furthest part, which is the outermost shell. So we can tell the size. Can you get my point? So for chloride ion, it is larger than sodium ion simply because they occupy different number of electron shell. So of course the size is different. Do you understand? So first of all, it's a regular arrangement. Second, why is it alternative manner? Alternative, one by one, okay? What I mean is green, purple, green, purple, green, purple, infinite, right? Lê Vũ Hằng, could you please help answer? Why is it placed in that manner, but not purple together and a green together? Instead, I place it like this way.
It is because when the sodium ion lose an electron for the chloride ion.
Yeah. So
therefore they stick together by a sodium ion and a chloride ion.
Okay, chloride ion and sodium ion, they will stick together intrinsically. Okay, that means spontaneously. So indeed, it is something what we call as attraction force. Okay, so altogether, it's time to know something about attraction and repulsion. Right? Okay, so in case we have got two charged particles of opposite charge, they will attract to each other. Attraction, you know it. Different, unlike charge attract, while the same charge. So what will happen? They will repel. They will repel. So we call that action repulsion. So no matter it is plus and minus or minus plus, right? They will also have an attraction to each other. Okay, so we would call this attraction a type of electrostatic attraction. Electrostatic 靜電吸引力 okay, electrostatic. So something about the charge. Okay, whenever I have got the charge of opposite charge, they will attract to each other intrinsically. So what will happen about this arrangement? So you may imagine the case is just an equilibrium state of placing the sodium ion and chloride ion together. Why is it an equilibrium? Because while whenever I arrange those sodium ions and chloride ions together, we need to consider both attraction and repulsion. Wait a minute, Mr. Chin. Isn't it only attraction? We have also got repulsion. Yes, we have also got repulsion. Could you please locate where? Where will you get repulsion as well in this diagram? Where? Where? For example, these, right? This repel. This one, these two will repel. Can you get my point? Whenever you see the ball of same color, they will repel. Have you ever followed that? Now, what will happen to the attraction force? Attraction force. Attraction force means this one is negative, right? So, what ions will that attract? Positive ion. So where you will find positive ions? Just next to it. Just next to it, right? So they will attract to each other. Can you get my point? So similarly, we may argue, Mr. Yin's minus is positive. Can we have attraction between these two? Yes, the answer is yes, but very weak because it's too far apart. Okay, so we will skip that. The weak attraction force, we try to think of attraction force which is very close. What else? What else? You may think of this, right? This one, these two also attract. And you may imagine that for these sodium chloride, you may altogether have how many neighboring positive ions are there? Do you know? How many neighboring positive ions are there for sodium chloride? Do you know? You don't understand? Now, it's time. I will give you some time to search on the web now. Now, you search on the web. I will teach you what to search. You search on the web. you type sodium chloride. And what's next? You just type one more important term, packing. Do you understand? And search it and try to see what you will have. But no, it's not that packing we are looking for. So what should I do? What should I do? It's not what we want. So what should I do? Ions? Yes, that's right. So remember, it's the manner of the way to teach you how to search on the internet, right? So you may find such. What will you get? My question is, how many neighboring sodium ions are surrounding one chloride ions? Can you search for me on the web? You may search. How many?
6.
Yes, 6. Which diagram will help you understand? Which one?
The first one.
Yes, the first one. So what is the difference between the first one and this one? Right? That you may see, very similar in the book. That two, which one we will call it as sodium chloride? Both will call it sodium chloride. Okay, but it is a different way to represent the whole thing. Okay, of course, this one you may see the ball and the ball we call the space filling model. This one, it will give you the reality, more or less reflect the reality, because they have considered the size, okay, of ions. But of course, I need to remind you, the ions, the sodium ions and chloride ions itself doesn't have any color. Okay. Don't tell me that chloride ions is green in reality, while sodium ions is purple in reality. They will help you distinguish, okay? Because the ions is too small, they will not have any concept of color, okay? So it is, but the size, it really reflects the reality. So this is a space filling model, but you cannot count. But once I use the first diagram, it may more or less help. Why? Because they would no longer consider the size of sodium ions and chloride ions. Instead, they use the two balls of the same size but with different color to tell the difference. Okay, so it will focus on what? It will focus the surrounding environment. Okay, so if I treat the red one is a sodium ion. Okay, so you may find that altogether the cube it is ever extending. Okay, in the x-axis, y-axis, and also in the 3D sense. So you may see the sodium ions, it is surrounded by 1, 2, 3, 4, 5, 6 chloride, the blue one. Similarly, if you treat the blue one as a center, chloride ion itself, they will be surrounded by 6 sodium ions altogether. Okay? Can you get my point? So we have got 6. But one question raised by Cyrus, you may easily find it on the web. You ask for the packing, the same for other ionic compound. Are they the same? Now, Mr. James, somebody may argue, right? Mr. James, for sodium chloride, because of that structure, right? We have got 1-to-1. Okay, you may count it as 1-to-1 because I just place it alternatively. So it is 1-to-1 ratio. Can you get my point? It's just 1-to-1 ratio. But can I search for some other thing else, just like cesium bromide, or cesium chloride, for example? Cesium chloride. Can you see? Is the packing the same? The answer is no. The answer is no. How do I know it's not the same? For cesium ion, it's now surrounded by 8 chloride ions neighboring. Okay? But instead of 6. So this is sodium chloride. Okay? It's sodium chloride, but for cesium chloride, it means different things. Okay? For cesium chloride, the packing is of this. So you may find that it's no longer 8 opposite charge ions surrounding one another. Okay, instead it is 8. And while the packing is more loose. So you may see that the packing is related to what? Do you know what's the difference? Sodium chloride and cesium chloride is also group 1 chloride. How come the packing is different? How come the packing is different? So what is the difference? I know that it's 1-to-1 rho ratio, right? Cesium ion or sodium ion to chloride is still 1-to-1. But how come the packing is different? Deng Junhei, do you know? So what is the difference between cesium ion and sodium ion?
Occupied electron shells.
Yes, the number of occupied electron shells, they are different. So as reflected by the size is different, okay? So relative size of sodium ions and chloride ions is much different than cesium chloride, because for the cesium chloride, the size of them, they are more or less similar. Okay, they are more or less similar, so they can do the packing like this, but the packing is rather loose. But once I change from cesium ion to chloride ion, what will happen? The chloride, the sodium chloride, the sodium ions, it is rather small, which can fill the hole between chloride ions. So what is the hidden message? The packing, it is more close. Okay, they're more closely packed together. So the packing is different. Just answer the questions raised by Jia Hongming. Do you understand? So remember, if you talk about packing, it's not just simple what you know in Form 1, because if you talk about Form 1 packing, you just have one size of ball, right? The ball of one size only. But if you want to talk about ionic compound, we need to consider both the cation and ionic size in order to tell the packing. Okay, is it just this? The answer is no. Have you ever heard of magnesium chloride? What happens to magnesium chloride? Magnesium chloride, it is another case. I would like to show you the other one. This one is better. Maybe sodium oxide. Can I see the Dutch? Yes, that's right. So if you talk about different material, they have their own different packing as well. If you talk about sodium chloride, so you may find the packing is a little bit different, while the packing way is different. I would like to show you this one. This one will best give you an example. It depends on different combination of cations and anions. Now, for example, if you have got calcium fluoride, you may find calcium ion and fluoride ion will have the number ratio 1-to-2. So you may find that, wow, calcium ion is less, fluoride ion is more, while the packing is different. Even though you talk about 1-to-1, for example, zinc blende, zinc sulfide is 1-to-1. So you may find that the packing is different. Can you get my point? So lithium bismuth, you may find that I will have got more lithium ion, right? So orange is more and then less for the blue one. While for sodium chloride is rather regular. Okay. Sodium ion and chloride ion placed alternatively in 1-to-1 ratio. So if you want to know more about packing, you may search it after today's lesson. You may search on the web and try to take a look more on that. Okay, for DSE, don't worry. We need not consider. We need not know too much about this. So what I want to focus is on this. So what is that? The ionic bond is found everywhere. It's just whenever we have got what? Positive ions and negative ions placed at the distance, they will attract. Okay, can you get my point? But it's not just 1-to-1 as a pair. So it can be this. It can be this. Okay, can you get my point? So it is a type of equilibrium 穩定 個平衡嘅狀態of state or in consideration of attraction and repulsion together to form this arrangement. So you may find sodium ion and chloride ion placed alternatively, but not sodium ion as a batch, chloride ion as a batch. Can you get my point? So that may be, so what is that attraction? That attraction is said to be non-directional. Could you please underline the term non-directional? 冇方向性嘅. So if you know anything about non-directional, you need to know the meaning of the term directional. Okay, so why is it non-directional? Because as said before, the type of electrostatic attraction is intrinsic. Whenever I've got opposite charge ions placed at a distance, they will attract, okay, irrespective of their direction. So we call that non-directional. Okay, to form that structure can be can extend infinite, right, in 3 dimensions. So we will call that a giant structure. Okay, or we call that lattice 晶格, or you talk about it as a giant structure. 巨型嘅結構啊. So we will call that structure giant ionic structure. All of you could you please mark it down. Giant ionic structure. Okay, so once I know it, you may know that, wow, what is meant by ionic bond? Mr. Chin, you still haven't told me anything about ionic bond. Well, ionic bond, what is that? Ionic bond, please put a star here. The ionic bond is a strong attraction force electrostatic force of attraction between oppositely charged ions. So what is meant by oppositely charged ions? Is it positive, negative, opposite charge, right? Or negative, positive? It's opposite charge. They will attract together. Because the particles, they are made up of ions. Okay, ions, which is the charge atom. Okay, whether it's positive charge or negative charge, we call that bond ionic bond. Can you get my point? So ionic bond it seems like this. So this sentence is a little bit misleading, but in the book very often you may see that. Take a look. The ionic bond is formed when the electrons is transferred from one atom to another, right? It seems like that, right? The electron is now transferred. But once I transfer the electron, how come I form ionic bond? It's misleading, right? The ionic bond is simply an attraction between oppositely charged ions. So never confuse that too. Can you get my point? Just stick back to this definition. Understood what I've just said? 離子鍵即係咩㗎？離子鍵即係咩㗎？大豪俊, could you please have a try on that? What's mean by ionic bond? To your understanding, ionic bond, what is that?
Yes, it is about when there were two different ions. These 2 different ions that they have, one have positive charge and negative charge, and then when they stick together, it is something.
Okay. Yes.
And there was a force between them.
Yes, there is a bond between them. Whenever I have got the ions of oppositely charged placed together, they will have attraction. Okay, so it is what is type of attraction? It's a type of electrostatic forces of attraction. 一個叫離子嘅吸引力，叫靜電吸引力。Okay, so you may find it on the this one we call it as an electron diagram. I must tell it is a little bit misleading. Okay, it's misleading to tell sodium chloride is of this. It's indeed it doesn't tell the true structure of sodium chloride, but in the DSE we often tell you how you can draw the electron diagram. You should know this. Do you understand? You should know how to draw this. If I ask you guys to write down the electron diagram for sodium chloride, you have to use how to draw this. Okay? How? You have to draw the all those electrons there, right? First of all. Second, can you tell me the arrangement of electrons? the electrons is now drawn in circle dot or a cross. Can you see that? Why will we need to use two type of symbols? Huh? This is for telling me that the electrons comes from sodium atom, right? Can you get my point? So you use that one as example. Do you know how to draw this? So finally, it's about the ion. The ion, you use a middle bracket and put a charge outside to tell. This is one way. Second, if you write down potassium oxide, sorry, you need to draw that too for sodium ion because the formula is K2O. So if you want to write down the electron diagram, you may use this method. Is also possible. Okay, Mr. Yu, you may say that, wow, it's too time consuming to draw such. Can I use lazier method? Any lazier method?
Only draw the outermost electron shell.
Only draw the outermost electron shell. Somebody would say so, but you have to stick back to the questions. If the questions can allow you to do so, you can only do so. Okay? But if the question doesn't allow you to do so, you have to draw the full. Any other lazier method which is qualified? Lazier method.
Potassium ion 前面加個2。
Yes, that's right. You used to put a 2 here. 2 here. The big 2 here. And then with a plus. With the potassium, 1, 2, 3, and 4. Oh, there should be 3. Because the last shell, the fourth shell is no longer have any electrons, okay? So originally is 2H1, it becomes 2H8. So you are going to draw such. And it is also allowed. Can you get my point? It's also allowed. So leaving behind is about oxide ion. So remember, it's very difficult. So you may do, if you want to use a cross to tell is sodium potassium ion. For oxygen to form oxide, you may either use the other sign, right? This is now I use a dot. And then dot, 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 and finally 2 crosses. The same thing. Can you see the difference? Can you see the difference? It's not just a number, but also the dot and cross. It can be interchanged, right? There's no absolute rule to tell cat ions you use the ball or dot or cross. Okay, whenever you make a easy distinguishing which ions is which is also okay. Yeah, questions?
Yes, I want to ask that if the potassium atom and the oxygen atom, can I write the 2 in front of the potassium atom instead of drawing 2?
Yes, that's right. This one. Do you see it on the screen? So you may find that you draw the 2 here, and then this and this. You need not draw the 2. And one more allowed method. It is also like this. Okay, I placed potassium ion and chloride ion alternatively, but you just use the same method, right? You need to draw the 2 potassium ion, right? So I can draw it as 2 potassium ion like this. Okay, just mark a 2, and it's solved. Okay, don't spend too much time on that, I must tell. How about calcium nitride? Even crazier, right? Calcium nitride, nitride, the formula is Ca3N2. So altogether 5 ions, right? So do I need to draw that 5 ions? This is one way. This is one way, one method. If you talk about another method, you may simply do what? How? Draw the calcium ion and then 2 plus, and then nitride ion 3 minus, and put a 3 here and then 2 here, and finish those remaining circles inside. It's one way. It's much easier, isn't it? Right? Don't spend too much time on that, on drawing the dot and cross. Please, don't spend too much time on that. It's not worthwhile to do such. Spend too much time on that. Now, it's your turn. It's your turn. Question 1. on practice 7.1, lithium combines with sulfur to form lithium sulfide. The particles in lithium sulfide are packed in an Ionic lattice. Draw the electron diagram. Now, this is what you are asking for, right? The electron diagram for lithium sulfide, showing electrons in the outermost shell only. Oh, good. Good. The question asking for, you can draw the final shell. So you may spend so much time on it. Anyone who can try on that? Anyone have got a pen? You may try it on the screen. No. But to start with, Lo Hong, could you please tell me the formula of lithium sulfide? It may help. It may help us draw that correctly. Lithium sulfide. How we draw that? Ionic, are you here? Lithium sulfide. The formula is how do you know? Oh, you good? Lithium Li2S. Yes, that's right. So Li2S. So formula is Li2S. So how will you draw that? In that, it is Li2S. So it is 2 lithium, and then sulfide ion is 2 minus, right? So how you draw that in the outermost shells only for lithium ion, right? You need not draw that outermost shell, right? You may treat it as 0, right? So you may simply skip it. How about sulfide? The outermost shell, 1, 2, 3, 4, 5, 6, and then 2 electrons, right? 2 minus. So you are going to show it intentionally that 2 crosses that comes from lithium atom. 2 lithium atoms, right? So remember to show this. Do you need to draw a circle? The answer is you may get rid of it. Okay, you may omit that. This one is also possible. 好唔好玩啊？呢個好簡單嘅係咪？ So B, describe the meaning of the word ionic lattice in terms of the type and arrangement of the particle present. As said before, what is that? What is ionic lattice? They will tell you an arrangement, okay, which contains what? Ionic lattice, right? So what does it mean by that? Yes, oppositely charged ions, okay, in an ionic compound. They are arranged in a regular arrangement, okay? They are packed together in a regular arrangement. Regular arrangement means ordered manner, right? So we call that ionic lattice, 正格. So for B, and the question 2, in a lattice of sodium potassium nitride, the ratio of potassium ion and nitride ions are 3 to 1. Why is the ratio 3 to 1? Why? Why? 黃耀朗.
Because the charge of the potassium is 1 plus, and the charge of nitrate is 3 minus.
Okay, with a charge of 1 plus, while for nitrogen, they will form nitride ions with a charge of 3 minus. But how come they should be in 3 to 1 ratio instead?
Each nitride ion need to gain 3 electrons in order to become stable.
Yeah, you talk about ratio, okay? The ratio of potassium ion. You may use that method, right? You talk about the number of electron transfer. Good. And also you may use the number of potassium ion to nitride ion. It is 3-to-1, so that something is balanced. What is that? The charge. The charges balance. You're going to balance the charge as reflected by the number of electron transferred. Okay? What's mean by the charges balance? The total positive charge equals the total negative charge. Do you understand? Understand? Okay. So this is what you know it about the ionic bond, right? Is the attraction between oppositely charged ions. Okay. So that's why here comes different types of ions to be introduced and different combinations that that you may know it in the late August, right? While you're having the supplementary lessons. So we can skip. Can we skip 7.4, 7.5, and 7.6? Okay, you may skip that 3. I would like to tell you what is that 7.4 polyatomic ion. So there may be a chance of having more than one atom stick together to form the overall charge. It is minus or plus. Most of the time, polyatomic ions, they are negative charge. But one exception, which is positive charge, what is that? That you may know?
Ammonium.
Ammonium.
Ammonium. Remember, ammonium, not ammonia. Be aware of the pronunciation. Ammonium ion, okay? Ammonium ion, but not ammonia. Huh? Ammonia is positive. So we call that this one, okay? Positive charge. This one you need to know. And the naming of ions, as I said before, okay? Metal ions, the name of the metal ions is as with the element. While for the non-metal, you need to change the name a little bit and end it with IDE. So you may say that oxide, chloride, bromide, iodide, okay? So this one you may know it. But for polyatomic ions, the rules that I've just suggested before, I don't want to mention here, right? You may skip it. Now, the naming of ionic compound, you should get note of that. I'll be prepared to have a quiz soon. And 7.7, okay? I don't want to mention too much about this because after you use that concept, you may help answer that. 7.7, I just introduced 7.7, and you are going to explain 7 to 8 by yourself, okay? So what is 7.7? 7.7, you talk about the ions. Indeed, some ions, they have got different, they have got their colors. Okay, so sadly, most of the ions in aqueous solution, remember the ions in aqueous solution, they are colorless except the following. Take a look on that. Potassium ion, potassium ion is colorless. Iron 2 ions is pale green. Iron 3, yellow brown. Copper 2 is blue. Permanganate is purple. Dichromate is orange. Okay. So you may get more. You may get more. Could you please search on the web? You need to tell me the following color. For example, what should be noted? Yes, iron, cobalt 2 ions. Do you know what's the color? Search on the web now. And what else? Permanganate, you talk about dichromate, you talk about chromate ion. Do you know what is the color of that? Chromium 3 ions. Manganese 2 ions. Can you tell me the color of those? And some special example is for zinc ions. Okay, can you please search for me the color of those? Cobalt 2 ion, manganese 2 ion, chromium ion. It is chromate ion. Do you know what is the color? And second, which ions are said to be colored? Can you generalize? Can you generalize? Do you know? Cyrus, do you know?
Transition metal.
Transition metal, yeah. Transition metal, ions of transition metals, they are colored. Except this one. Do you know that too? What is the color? It is colorless. Not white, okay? Remember, if it shows no color, you tell it colorless, not white. Can you tell the color of those? Now this color should be memorized. You have to memorize the color corresponding with the ions. How about that? Cobalt 2. So what is that color?
Blue.
Light
Cobalt 2.
red.
Dark red, or in this pink, right? It depends on concentration. Manganese 2. Manganese 2, do you know what is the color? It's pale pink, very pale pink, or even colorless, right? Because of the color intensity is low. And chromium 3, do you know? Chromium 3. Chromium 3, what is the color?
Green.
Yep, green. Good. How about this one? Chromate. Chromate is not dichromate. Chromate. Chromate ion.
Yellow.
Yellow. Good. So that for that cases, please memorize the color. Okay, this is frequently tested in DSE. Please memorize this page. And before we end up the lecture, I would like you guys to keep this in mind and try to relate to the following cases. Okay, and try to give me your understanding. Okay, I will show you the YouTube video as well to show you the relevant experiments. It is on the migration of ions. Okay, so why do we need to know ions, right? Is because of the gemstones, the 晶石啊、寶石啊. So you may find different colors. So indeed, it contains several amounts of the transition metal ions. So you may see it colored. Even though you talk about yellow, purple, etc., there may be some chemical inside, which will make it colored. So it is for your take-home exercise. You read the 7.8. You read 7.8, and I would like to test for your self-study skills. Try to take a look if you can manage that part by yourself. 7.8 together with I will show you some YouTube video to tell you something similar, and try to see that why does it happen? Why is that such an observation? So what is that? We're going to have a glass slide, right, with a filter paper. One filter paper is soaked with some solution. Okay, soaked with some solution, and you are going to refer to the paragraph. And I place a crystal of potassium permanganate. I connect into electricity and try to see finally there is a migration, the movement. There is a moving of the purple spot towards one side. Tell me the observation and tell me why is it like that. And if I change this crystal to other colored ionic compound, so what will happen? Okay, so this is what you may need to know. And the other example is a migration of copper ions and chromium ions with a similar observation, and try to see if you can handle. And 7.2, take home and do it as a homework, and we'll try to check it. Okay, we'll try to check it when we meet 2 days later. Okay, is that clear? We will see you guys this Thursday, is it? Is it Thursday? What do you think about today's lecture? Easy, difficult, easy managed, or what? It may a little bit more difficult than the previous lesson, I must tell. Okay, a little bit more challenging. So it's your turn. Try to understand this one by yourself. Okay, and we will end the lesson. We will end this chapter very soon. Okay, next lesson we will end this chapter. And one more thing is about the quiz arrangement. I would like to type the quiz arrangement onto the Google Classroom, and you may need to memorize those ions. Have you all memorized ions, the formula of ions? And you have to memorize the formula of ions such that you can write down the formula of ionic compound. Okay, is that clear? So we have got a quiz very soon. Please memorize the periodic chart of ions. Okay, see you guys. Bye bye.